what we saw on the first part of impulse from the point of view of Newton's law is how can we calculate, what are the ways so that we can calculate the change of momentum or the impulse. And here we mentioned the 4 ways on how to calculate the change of momentum or the impulse as a general one, as an explanation. What we will see now is examples on how can we calculate it and what is the best method to use for different situations that we have. So if we know the initial momentum and final momentum of an object as a vector quantity, so if I'm saying to you, and this is example 1, if I'm saying to you that initially an object is having a momentum that has a value of 50.3 kilograms meters per second going east, and then as a result of an object colliding or whatever is the situation, then after a certain time the object is having a momentum that is with 62.8 kilograms meters per second going north. What is the impulse or what is the change of momentum? And the best way to do it is to use the fact that the change of momentum is simply being delta is final minus initial. So it will be P final minus P initial. Vectorially, what we will have is that momentum initial is going east, is something like this. And momentum final, it's 62.8 kilograms meters per second going north. So vectorially, what we will have, since we start with P final, even if we say either the closed polygon one or the parallelogram method, whatever method you prefer graphically, we will have something like this. For P final is going north. Now, if we were doing P initial, then we will go in this direction. This will be P initial. However, since we have the negative P initial, then we will go in the other direction. So this will be negative P initial, which tells us that the change of momentum will be this vector here. Okay, so this is graphical. Now, to identify the value of the change of momentum along with the direction, so the magnitude and the direction, what we will do is we will draw the table of component, or since we are going straight north and west on this case, we can even do the right angle triangle situation solving for the hypotenuse. So the magnitude of the change of momentum will be the square root of P final squared, magnitude of P final squared, plus magnitude of P initial squared. Or we'll have, what is it, 62.8 squared plus 50.3 squared, and the whole thing square root. So when we enter it in your calculator, you will have, considering it into the correct sig digs, will be 80.5. And now, as we said, kilograms meters per second is the same as newtons times seconds. And since we are talking about the change of momentum or the impulse, we'll say that the magnitude is 80.5 newtons times seconds. And then the direction, which is the angle theta. And I'm just taking this angle, but you can take the angle with west axis, will be the same thing, will be the inverse tangent of P initial, magnitude of P initial over magnitude of P final. Or inverse tangent of 50.3 over 62.8. Make sure that the mode of your calculator is on degrees, and then you will have 38.7. So now the change of momentum for this situation, when one object has an initial momentum of 50.3 going east and 62.8 going north, will be 80.5 newtons times seconds at 38.7 degrees, and this will be west of north. The same thing is when we are dealing with 1D. So let's suppose that we have a situation in which the initial, example 2, the P initial is 12.3 kilograms meters per second going east, and P final is 15.5 kilograms meters per second west. So it's the same as saying that you have an object that you are throwing into the wall, and you are, as it is hitting the wall, is possessing a momentum of 12.3 kilograms meters per second, and then it is bounced back with a momentum of 15.3. Then the change of momentum or the impulse will be P final minus P initial. And since this is a 1D situation, what do we do in 1D situation? We assign a positive direction. Assign a positive direction. And then we add with positive and negative numbers. So vectorially, the situation will be something like this. P initial will be 12.3 kilograms meters per second, and P final will be 15.5 kilograms meters per second going west, while this one here is going east. If we are drawing the vectorial difference of those two vectors, then we'll start with P final. As being 15.5 kilograms meters per second going west. And now if we were drawing, or if we were plotting into this the positive initial, momentum initial, then we would have gone in this direction. So this will be positive P initial. Since we have to subtract, then what we do is we have the opposite of the P initial, so it will be negative P initial, which is 12.3 kilograms meters per second, now going west as well. And this tells us that the change of momentum is this vector here. But even mathematically, we're using the fact that we are assigning a positive direction and then we are adding with positive and negative numbers, will give us the answer that the vector or the graphical way of subtracting those two vectors represent. So if I'm assigning as a positive going east, you can assign it even going west, will be the same thing. Then the change of momentum being P final minus P initial, and the positive direction being going east, sorry, then P final going west will be negative. So negative 15.5, and I'm ignoring the units here because now we know, minus, that is from the formula, initial going east has the same direction as the positive direction, so then will be positive 12.3 kilograms meters per second, and then you will have an answer that is 15.5, negative 15.5 minus 12.3 will be negative 27.8 kilograms meters per second. However, since we are dealing with change of momentum, we will identify it by writing the units of newtons times seconds, which again are the same as kilograms meters per second. Or we can say that is 27.8 newtons times seconds going negative now. If the positive is going east, the negative will be going west. Even if you have something like both of the initial and final are forming a 2D, so you can say that P initial is 20 kilograms meters per second at 30 degrees north of east, and P final is 18 kilograms meters per second at 25 degrees south of west. When we are finding the impulse or the change of momentum for this situation, graphically what we will have is, for initial, we will have a vector that looks like this, P initial, with a 30-degree angle with the east axis, and for final we will have between south and west, so is a vector that looks like this, P final, and the angle with the west axis is 25 degrees. So now when we are adding those two vectors graphically, what we will do is we'll adding, we actually are subtracting, not adding. So we'll go P final is here with a 25-degree angle, and then if we were doing the P initial, then we would have gone through the north and east axis. Since we are doing negative, then we extend it in the opposite direction. This one here is 30 degrees. And then we create the parallelogram. So 25 here, 30 here. We create the parallelogram, and the diagonal that goes from the same starting point to the same ending point will be the change of momentum. If we are doing this using the table of components, then what we will do is we'll create the table of components in the same way as we have done for any vector, stating that we'll start with momentum final and then the opposite of momentum initial. And then as the third row, we will have the change of momentum or the impact. Now, when we know the mass and V initial and V final, what we will do is we will be able to calculate the impulse or the change of momentum. It's the same thing. I'm repeating it over and over just to emphasize that it's the same thing. So a very common question on how to calculate impulse is when you have an object, let's say you have a ball with mass of 1.23 kilograms, that you are hitting it into a vertical wall, and as it is hitting the wall, it is going with a velocity of, let's say, 5.80 meters per second going east. And then it is rebound from the wall, so it's coming back from the wall with a velocity of, let's say, 4.20 meters per second. When we are saying rebound, what do we mean is it is coming on the opposite direction as to what it is going to. So if it is going east, then rebound will be west. If it is going north, then rebound will be south. Okay, so even if they are not stating the direction of the final velocity, as I think I said 4.20, then the fact that they are stating rebound means that the direction of this velocity is the opposite of what it is going in, the opposite of initial, and the opposite of east will be west. So now when we are calculating the change of momentum, the most easy way to calculate it out of those four ways will be to say that is mass times a V final minus a V initial. Now, again, what this change of velocity in this situation being a 1D situation will be something like this. V final is going west, and it is 4.20 meters per second going west. And negative V initial will be west as well. So negative V initial will be 5.80 meters per second going west as well, which tells us that the change of velocity for this situation will be going west as well. So graphically, even mathematically, being a 1D situation, we will assign a positive direction. And now, just so that I can stretch your brain a bit more, I will assign as a positive direction going west. So I will say that, no, going west is positive. You can assign any direction as a positive direction. This is what I'm trying to achieve with assigning positive going west. And then I'm adding with positive or negative numbers. So now, the change of velocity is being V final minus V initial. This is like any change, is always final minus initial. Now, I'm saying that the positive is west. V final as 4.20 meters per second going west, will it be positive or will be negative? Will be positive meters per second. Minus, that is from the formula, and then 5.80 meters per second going east in comparison to the positive going west will be positive or will be negative? Will be negative. So 4.20 and 5.80 in your calculator will be positive 10.0 meters per second. And what positive means in our situation is going west. So this is the same for our situation, since we are saying that the positive is going west, is 10.0 meters per second going west. Understand? And now when we are calculating the change of momentum or the impulse, we will have mass times the change of velocity, which will be 1.23 kilograms times 10.0 meters per second going west, which is 12.3 newtons times seconds. I change it now into newtons times seconds, even though that newtons times seconds and kilogram meters per second are the same thing, going west. And this will be the change of momentum or the impulse. So now we will see an example in which we will use the graphing. So let's suppose that we have a situation like this, when we have a force in newtons and versus time graph in seconds. Just for simplicity, I will just do force newtons and seconds, and then I will show you what do you have to do when you see a different units. And the graphing or the relationship between force versus time will be something like this. So you will have a positive 12.3 newtons, and then this is a constant time up to let's say 3.50 seconds. So now the area, we said that the area under the graph, which is this area here, will be the change of momentum or the impulse. Now, when we are doing that, so area equals to the change of momentum. When we are doing this, you see that the force is identified as a positive. And I told you, even when we were working with vectors, that in order to state that you are dealing with a vector, even when it is a positive one, you have to state the sign to identify, to tell the reader of your paper that what you are dealing with is a vector quantity. So now this positive sign, we do not know what does it represent. Does it represent going north, east, south, west, or a direction in between those axes? What we are assuming here is that it's a positive direction. Whatever is the positive direction that the question is either assuming or stating or letting us know, or even saying that it's a positive direction. So we don't worry too much what is that positive direction, but what do we say here is say that this is the area under the graph. And since this graph, or what it is from the graph, from the line, to the horizontal axis, which is time axis, is a rectangle, then the area under the graph, based on the formula, will be of the calculating the area of the rectangle, will be base times height. And now the base will be 3.50 seconds, and the height will be positive 12.3 newtons. And again, what is that positive? We don't worry, we don't care, we are not interested of knowing. We just know that this is a positive, and that is enough for us to state what is the impulse. And when we are entering it into our calculator, we'll have a positive 43.05 newtons times seconds, and considering it writing with the correct significant digits will be positive 43.1 newtons times seconds. What is that positive? Whatever the positive is that the question is assuming, letting us know, or stating that is the positive direction. So when we have now, again, what we are doing is we are combining the force net times or force times time is equal to the change of momentum with the graphing. And on this example here, what we will see something like force on newtons and time on seconds. And as a graph, you will see that you have a triangle like this. And this is F max. And this is 2.80 seconds. Now, what do we know is that the change of momentum is positive, let's say 80.4 newtons times seconds. And whatever is the positive, again, we don't worry, it's not our focus. Okay, so now, since the graph is given, then we can say that the area under the graph is the impulse. Area is equal to impulse. And since the shape that we see is a triangle, then we can say that this is 1/2 base times height. Now base is this one, 2.80, and height of this triangle is F max. Okay. On the other hand, what do we know is that the change of momentum or the impulse is given to us to be 80.4 newtons times seconds. So then from here, the 1/2 times 2.80 times F max that we don't know what it is will be equals to positive 80.4 newtons times seconds. And from here, we can find that F max is equal to positive 57.4 newtons. And even if you work with the units, you will find the units of Newton that are left here. Okay, make sense?